Okay, so with this video, we're starting a new chapter, um, but ultimately it is related to the previous chapter, the systems of equations. In this first section, we're being introduced to what's called a matrix. Okay, and it's sort of a rectangular group of numbers, an array, if you would, and they're real numbers. Okay, and they're arranged in rows and they're arranged in columns. Okay, they don't have to be in the shape of a square. They can be rectangular. All right. Um, we refer to the size of a matrix with the rows first and then the columns second. And so these are the rows M, and then these are the columns N. Okay, and so it starts out with a row label and a column label 1 1, and so A11 is simply telling you that it's in the first row and the first column. Okay, and if it's sort of strange to you that the row number comes first and the column number comes second, then you're not alone. I pretty much have to remember that row and column RC is not in alphabetical order, just to keep track of which number actually comes first. So if we just pull out some random number from this matrix, say A43, then you have to know that the subscripts are labeled according to the row first and the column second. So this would be the number in the fourth row and the third column. Okay, and the size of a matrix, it can have different number of rows and columns. It doesn't have to be a square matrix, and so we refer to the size as M by N. And we'll look at some examples of matrices below, and we'll determine their size. The principal diagonal is going to be important in relation to these matrices, and that's just simply the elements of the matrix where the row and the column are equal. In other words, if you start at the very top left and you go down 1 over 1, then you can identify the principal row, or the principal diagonal, sorry. Okay, so you just go down 1 over 1, down 1 over 1, and you'll pick out the principal diagonal elements of a particular matrix. Okay. When you have a matrix with one column, it's called a column matrix. If you have a matrix with only a row, then it's called a row matrix. Alright, so in example 1, we want to determine the size, and then we want to identify the principal diagonal of each of these matrices, A, B, C, D, E, and so on are the names of the matrices. Okay, A is 1, 2, 3 rows, and 4 columns, 1, 2, 3, 4. And so that tells us that this is a 3 by 4 matrices. B has 1, 2, 3 rows, and 1, 2, 3 columns. So B is a 3 by 3 matrix. C has 2 rows and 1, 2, 3 columns. So C is a 2 by 3. Rows first, columns second. D, we have 3 rows, and then we have 2 columns. So D is a 3 by 2. E is a 2 by 2. F is a column matrix, okay, because there's everything's in one column. And so we would write the rows first, 1, 2, 3, 4 by 1 column. And G is a row matrix. And so this would be 1 row by 4 columns. Okay. And now we'll just go back and pick out the diagonals of each matrix. So for A, the elements of the principal diagonal of A, we start at the upper left, the very top and farthest to the left, and we go down 1 over 1, and so we're just simply going through the matrix diagonally. Okay, and since this has a different number of rows versus columns, then we're not gonna have a principal diagonal that goes from one corner to the other. 2, 3, and 8 make up the principal diagonal of A. For B, it's a 3 by 3, so we'll go from one corner to the other. There's our principal diagonal, 1, -3, and 1. C, we only have 2 numbers in the principal diagonal, 2 and 3. D, 1 and 3. E, 2 and 0 make up the principal diagonal. F, there's only 1. Okay, we can't go down 1 and over 1. There is no second column. And then for G, there is no second row, and so 4 ends up being the only number in the principal diagonal of G. Okay, and then we have a note here at the bottom. You can have a matrix with only one element. Okay, this is a 1 by 1, 1 row, 1 column, and that would be equal to just the number inside of the matrix. So you can write it with the matrix bars around it, or just as the number itself. Okay, what this part at the top of page 122 is saying is that if two matrices are equal, then they have to have the same number of rows and columns, and every element has to be equal. So for instance, if I said these two matrices were equal, 1, 2, 3, 4, this is a 2 by 2 matrix on the left side of this equal sign. And so if this other matrix is equal to it, then this has to be a 2 by 2 matrix on the right, and then all of the numbers have to be identical. And so this one on the right has to have 1 in the first column and row, 2 in the second row, first column, 3 and 4. They have to be identical. Okay, so in example 2, if we're told that this matrix on the left is equal to the matrix on the right, first thing you could check is that they're the same dimensions, and so this is a 2 by 2, and on the right we also have a 2 by 2. Alright, so that has to be true, and we're not really questioning the truthfulness of this equation. It's just one thing that you can check out, but here we would know that this first element of the matrix has to equal a -2. So that's the only possibility. If these two matrices are equal, then x has to be a -2. And then likewise, y minus 2 has to be equal to the element in the other matrix on the right that is in the second column and second row, and so y minus 2 has to equal 1, and so y has to equal we add 2 to both sides, y has to equal 3. And then x, we said, has to equal -2. Okay, so it's pretty simple. We match the elements of each matrix, and so each one of these we could possibly come up with 4 equations because there's 4 elements in a 2 by 2 matrix. So for the next one, 2x plus y is in the first row, first column. And so it has to equal the first row, first column of the second matrix, 5. And in this case, we have an equation with 2 variables, and so if we're going to solve this for x and y, then we have to have another equation. 2 variables, 2 equations, and we have that with the second row and second column. We have 1 has to equal x minus y. So x minus y equals 1. It's already set up for elimination because the y's of the equation have equal numbers but opposite signs. If I added the 2 equations, the y's would cancel, and I'd end up with a 3x equals 6. And now if I just simply divide both sides by 3, I get x equals 2. Alright, and we were told to find x and y, so x equals 2. Then I can take either one of these equations that I had in the beginning, plug in x, and solve for y. So this is 4 plus y If I subtract 4 from both sides, I end up with y equals 1. So x is 2, y is 1. Okay, some operations that we're going to talk about with matrices. We have sum and difference, and we have scalar multiplication. Okay, and then we have a new one that we typically don't do with real numbers. Okay, you already know how to add, subtract real numbers, multiply, divide. We can do some of that with matrices as well. But a new one is the transpose. Okay, and we sort of rearrange the matrix elements when we calculate the transpose of a particular matrix. So in example 2, we're going to do just that. A plus B. In order to add two matrices, then they have to have the same dimensions. And if you'll check up top, we're given A and B, and we have 3 by 3, 1, 2, 3 columns, 1, 2, 3 rows for A and B. So to add these, we would end up with a 3 by 3. Okay, and we'd simply take the elements that are in the same position. So first column, first row, plus the first column, first row of B. So for this upper left element in A plus B, we would write 2 plus 1. There's the 2, there's the 1. Okay, if I go over to the right and I add the second column, first row, indicated with a square, then here in the middle I would have a negative 1 minus 3. Alright, and these are separate calculations. 2 plus 1 is separated from negative 1 minus 3. And then here 5 is in the third column, first row, and likewise negative 6 is in the first row, third column. So this would be 5 minus 6. And we'd simply run through the rest of the numbers in the same fashion, adding the numbers in the same position. So negative 2 and 4, 3 minus 3, 4 plus 2, 1 plus 5, negative 7 plus 8, and 8 plus 1. And so the matrix A plus B would end up being 3, a negative 4, a negative 1, 2, 0, 6, and 6, 1, 9. Alright, and you can actually do this with your calculator, but for right now we'll just add and subtract these by hand, and I'll show you how to do it with your calculator later. Alright, so C and D, we want to subtract them, and so we have to go up here and check the dimensions. We have rows 2 and columns 3, and likewise for D. So they have the same dimensions, 2 rows, 3 columns, and that just means that we can add and subtract them. And in the case of B, we're subtracting them. So we first we take an element from C. I'll start at the top left, 2, and we'll subtract the top left number in D. So 2 minus 1. Then we have negative 1 and then minus a minus 3. And then the third column, first row, 5 minus 5. Then we have negative 2 from C, minus 4 from D, 3 minus a minus 3, okay, remember we have to subtract the element in D, so the last one, 0, the bottom right, and then minus 8, the bottom right of D. So if we add or subtract two matrices that are 2 by 3, then we end up with a matrix that is 2 by 3 as well. So 2 minus 1 would be 1. A negative 1 minus a minus 3 is 2. 5 minus 5 is 0. Negative 2 minus 4 is a negative 6. Then 3 minus a minus 3 is a plus 6. And then a negative 8. Okay. E is a 3 by 2. Alright. And then you see D here, and you know that D is a different dimension than E. D is a 2 by 3 where E is a 3 by 2, so the numbers are swapped. But you don't actually see D by itself here. It has a little superscript T, and that means that we want to take the transpose of D and add it to E. Alright, so what is the transpose of D? Well, we swap the rows and columns. So in other words, this column is going to become a row of D transpose. So instead of writing 1, 4 vertically, we start with the upper left and write 1, 4 horizontally. It becomes a row. And so the second column becomes the second row, -3, -3. And then the third column becomes the third row, 5, 8. Another way to look at that is to say that, okay, let's just pick out a number 5. Well, 5, we could say, is the element of D, where the labels, the subscripts, would be, let's see, the first row and the third column. Taking the transpose of D swaps these numbers, and so 5 would become the element A sub 3, 1. And so this means the third row in the first column, and that's exactly where it landed in D transpose. Okay, so you swap the subscripts. Alright, and now you see that D transpose is a 3 by 2, just like E is, and so we can add these two together. And so let's see, we just simply add the numbers. The order of addition doesn't matter. We would get 1 plus 1, -5 plus 4, 4 minus 3, -3 minus 3, 2 plus 5, and -1 plus 8. So to carry out the addition, we'd have 2, -1, 1, -6, 7, and 7. And now, let's see, we have A, which is a 3 by 3, plus D, which is a, let's see, 2 by 3. Okay, this does not exist. You cannot add these two. They're different dimensions. Okay, different dimensions. Alright, E, we have E minus C. And so let me see if I can squeeze this in to the page. E minus C, we can't do that either. This does not exist. E is a 3 by 2 and C is a 2 by 3. Okay, these are different dimensions. Okay, so whenever I went to subtract a number from 5, well, let's say, hold on, let's say we took E. Okay, E comes first in the subtraction. Well, I take 2 and I subtract what from it? Because 2 is in the first column, third row. C doesn't have a third row. There's no numbers listed there. I can't just say it's 0. Okay, this number in C does not exist. Okay, so you cannot subtract matrices with different dimensions. We'll check the next one. Let's see, 2a minus 3b. And what we're doing here is we're multiplying a and b, and then we're subtracting them. So first we'll multiply a by 2. Okay, this is going to be 2a. Okay, and then we'll subtract 3b. Alright, so I have to move back up here so I can see a and b. Well, 2a, we just simply go through each element of a and multiply it by 2. So first row, first column would be 2 times 2. And then we'd have 2 times negative 1. Then we'd have 2 times 5. 2 times a negative 2. 2 times 3. 2 times 4. Every number is multiplied by 2. Okay, and here's my subtraction symbol between the two matrices. Same case for b, except we multiply by 3. So 3 times 1, 3 times a negative 3, 3 times a negative 6, 4, negative 3, 2, 4 times 5, or where did that 4 come from? I'm trying to go too fast. It should be 3. Three times 8 and 3 times 1. Okay. Well, now I'll just simply go back and replace these with, I'll actually carry out the multiplication, which you probably could have done that in the first place. So we end up with 4, negative 2, 10, negative 4, 6, 8, 2, and negative 14, and 16. Okay, this is 2a, and then we subtract from it 3b, which is 3, negative 9, negative 18, 12, negative 9 again, 6, 15, 24, and 3. And I want to subtract these numbers. So if I do this in my head, I would say 4 minus 3 is 1. Negative 2 minus a minus 9 would be 7. 10 minus a minus 18 would be 28. Okay, minus a minus 18 is plus 18, so 10 plus 18, 28. Negative 4 minus 12 is negative 16. 6 minus a minus 9 is a positive 15. 8 minus a 6 is 2. 2 minus a 15 is negative 13. Negative 14 minus 24, negative 38. And then 16 minus 3, 13. And so this would be our final matrix. This is 2a minus 3b. Okay, with a and b being matrices. Alright, the product of two matrices. Well, the rows and columns have to be, let's see, okay, with the order of the matrices in the product, um, we have to have the columns of the first matrix match the rows of the second matrix. And so sometimes we can't multiply in both directions. That means that matrices aren't always commutative with respect to multiplication. A times B doesn't necessarily have to equal B times A, and you may not be able to calculate both of these, alright, because the columns of the first one has to match the rows of the second. Alright, so let's see. They list a special case here where we have, let's see, a 1 by P, this is A, and then we have a column matrix. Okay, so we're saying A times B. I'll put a dot here. A times B. So if A is a row matrix, then it has one row, and then it could have any number of columns. But then if we multiply that by B and it's a column matrix, then we have to have the same number of rows, and then with it being a column matrix, we would have the second dimension 1. Okay, if you multiply a row times a column matrix, you end up with a single number, a 1 by 1 matrix. Okay, so two matrices can actually produce a single number. It's sort of a special case. And again, the columns have to match the rows, or else you can't multiply the two matrices together. Alright, so how do we multiply these together? Well, we calculate this. It's sort of a long drawn out process, but what we do is we multiply the first column by the first row in the second matrix. So this would be 4 times 2, and we don't stop there. This would be the first element of whatever matrix we would get by multiplying these two matrices together. And so we would now add the next product of the -1 and the -3, the second column times the second row. So this would be -1 times -3, and then we would add to that the third row times the third column, okay, the 5 and the 1, 5 times 1, and then we multiply the 7 times the 6, and we would add all of that together, and this would make one element of the product of the two matrices. Okay, so 4 times 2 is 8, plus -1 times -3, 3, plus 5, plus 42. So you can see if the matrices that you're multiplying together are a lot bigger, okay, they're not just a row and a column matrix, then it could be quite a calculation to figure out the product of two matrices. Here we just did one element of the matrix, and it turns out that this is the only element of the product. So 8 plus 3 is 11, plus 5 is 16, and then we get 58. Alright. And again, I can show you how to do this with your calculator, and I'll probably do that later in the chapter. Example 4 says, let the row matrix N, 4, 2, and 3, Okay, 4 and 2 and 3 are all in different columns. So this is a row matrix with 1, 2, 3 columns. It is a 3, I'm sorry, it is a 1 by 3. Represent the number of pencils, erasers, and pens. So the first column is pencils, second column is erasers, and third column is pens. So 4, 2, and 3 that a student purchased. And then we have a column matrix, represents the amount of money, and so this is the price of a pencil, and then $1 is the price of an eraser, and $3.50 is the price of a pen. Compute N times P. NP. Okay, if we wrote that out, it would be 4, 2, and 3. And then we'd multiply that by the column matrix, 150, $1, and 350. Alright, and again, here we have 1 by 3, and this is a 3 by 1, and so the columns of the first matrix match the rows of the second one. The 3's match. Okay, and that has to be true in order to be able to carry out this product. So, how much does all this cost? We would multiply 4 times 1.5 and then add 2 times 1 and then add to that 3 times 3.5. Alright, and so we have to match the columns and the rows, and so those match, and so we're done with those. Well, what dimension matrix are we going to end up with when we actually carry out the product? Well, the rows and the columns are left 1 and 1, and so we're going to end up with a 1 by 1. We're only going to get a number here, a single number, and 4 times 1.5 would be 6, then plus 2, the cost of the erasers, and then 3 times 3.5, what do we get? 9 plus 1, 10.5, $10.50. We add all of this up and we get $18.50. Okay, a single number. And that's what happens when you take a row column or a row matrix and multiply it times a column matrix. You get a single number. Okay, so let's see, it says a bunch of stuff about how to go about multiplying matrices, and it repeats that A has to have the same number. You can see that you have P for columns in A and P for rows in B. So to multiply A times B, columns match the rows. Okay. And so this part we're actually going to do with calculator. But first we're going to go through and decide whether we can actually calculate all of these products. Can we calculate the product of BA? Well, we have a 3 by 3 multiplied by a 3 by 3. And so the columns equals rows. So yes, the product exists. Alright, what about AB? Well, it's a 3 by 3, so if we swap them, we still end up with the columns of the first equals the rows of the second. Okay, column of the first, that's what we did in the first part. Column of the first equals the rows of the second, and we go from left to right. And so once again, Yes, this product exists. What about B, C? And I'll put a check mark up here so we'll know which ones we can calculate. BC, well, we have a 3 by 3 is the dimensions of B, 3 rows, 3 columns. And C is, let's see, 2 rows, 3 columns. And these don't match. Okay, column of the first does not equal rows of the second matrix. Okay, so no, product does not exist. So I'll cross this one out. What about CD? Well, C is a 2 by 3. And D, where is D? I don't see a D up there. Well, that one's going to be easy. D doesn't exist, so we can't multiply that one. And I'm assuming, well, let's just say this was supposed to be D. That's probably what happened, and this last one was supposed to be E. Okay, we'll make that little switch. Hopefully that doesn't mess us up. So we'll reconsider C times D. If this fourth matrix is D, then what we have is a 2 by 3 for C times a 3 by 2, and these columns of the first equal the rows of the second, and so this one exists. I crossed it out there, so let me erase that and check it. So that checks. Alright, so let me clear this other stuff. I've got my list where I checked them. Check marks in my X's. So what about CB? Okay, C again is a 2 by 3. B is a 3 by 3. And so columns of the first match the rows of the second. So yes, that one checks. DE, can we calculate a product here? Well, D is a 3 by 2, and E is a 2 by 2, and so these match. Column of the first equals rows of the second. And finally ED, we've got a 2 by 2 times a 3 by 2, and no, okay, these do not match. Columns of the first does not equal rows of the second. Alright, so we'll cross this one out, and we're left with 5 that we can actually compute. I'm going to pick the smallest one, and then I'll show you how to do the larger ones with your calculator. Okay, let's see. We'll do DE. We have 1, negative 5, 4, negative 3, and 2, negative 1 times 2, a negative 2, 3, 1, negative 1, and 0. Okay. Alright, we're going to need a lot of space here. This is a 3 by 2, and this is a 2 by 2. So these two tell us that we can, the inner ones tell us that we can multiply because they match, and these outer ones, outer dimensions, tell us the product dimensions. And so we're going to get a 3 by 2. So 3 rows. I think I have enough space here for that. And then 2 columns. I'll separate this into columns and rows. Okay, so 1, 2, 3 rows and 1, 2 columns. Alright, we start out by taking the first row and multiplying it by the first column. So 1 still matches with the -2, the same position there. So we say 1 times -2. And then we add to that the second element of the row and then the second element of the column multiplied. So this would be a -5 times 3. Okay. Now we go and we do the same thing. We pick up the first row of the first matrix and now we multiply it by the second column. Okay, so first row, second column, first row, second column fills in this position. First row, first column filled in the 1, 1 spot. The first row, first column. Alright. So 1 times a -1 plus -5 times 0. Alright, and now we skip down here to the second row of the first matrix. So the second row, and we're going to multiply that times the first column, and so we're going to fill in this entry in our product to 1. Second row, first column. So 4 times a -2, and then we add to that a -3 times a 3, and we've completed that one. And now we take the second row, row goes first, times the second column, column goes after the rows. And so this is the position 2, 2. Alright, so when we multiply this second row by the second column, it's going to give us this number 2, 2. So 4 times -1 plus -3 times 0. And finally, the third row times the first column is going to give us this position 3, 1. So 2 times -2 plus -1 times 3. And then we have the third row, the 2, -1 times the second column of the second matrix. So 3, 2. Third row, second column, 2 times -1, and then -1 times 0. And so to make a long story short, we do all of these calculations. In the second column of the product, the 0 knocks out the second number in the sum, and so we have a -1, a -4, and a -2. And then here the first column is a little more difficult to calculate, but we have a -2 minus 15, -17, a -8 minus 9, -17, and then we have a -4 minus 3, -7. And so the product is a lot more work to calculate with respect to the addition or subtraction of two matrices. It's pretty tricky, and if you're going to do it by hand, you definitely need to get enough practice. But now I'm going to show you how to do it with your calculator. So what we want to do is we want to first go to the matrix menu, second in this button here with the X to the -1 power. Okay, you can read matrix in blue letters above this button. So we have to hit second and then this key. That takes us to the matrix menu. Here are all the names, and we can select these names and take them to the home screen. But what we want to do is edit these names, and we have A, B, C, and D. That's typically how we name a matrix. So let's edit A. We want it to match the A in the workbook. A in the workbook is a 3 by 3, so we'll enter the dimensions, rows first, columns second. And once we do that, we have a 3 by 3 matrix that's filled up with zeros, and now we need to go back and change those numbers. -2, 3, 4, 1, -7, and 8. Okay. And we hit enter, and now we go back to the matrix screen, and you can see that when we edited, we didn't have to click save or enter. Well, we entered, but we didn't have to save or anything special. We just simply went back to the matrix menu, and you can see here that for in the position A, matrix A, it's got this 3 by 3 matrix that we just entered. So we'll go to edit, and we'll do the same with matrix B. Okay, B is a 3 by 3, so we enter the dimensions of the matrix, and now we go through and type in all the elements. -3, -6, and it goes row by row from left to right. So 4, -3, 2. I don't actually have to arrow over. You can if you need to. If you have to go back and fix a number, you can arrow left, right, up, and down. But I'm on the third row, and so I type 5, enter, 8, enter, 1, enter, and B's in our calculator now. So I'll hit second in matrix, and you can see that beside the name for B, it has 3 by 3. So it accepted our numbers. And for C, let's see. Well, we went to B. Okay, let's go back. There we go. We need to go to edit and C. C is a 2 by 3, 2, -1, 5, -2, 3, and 0. Alright, we've got 2 more left. Remember this one in the workbook, E, we just called it D. Go to edit, D, click enter, and D is a 2 by 3, 3. Oh, I'm sorry, I got the dimensions wrong. It's a 3 by 2. And so we have 1, a -5, a 4, -3, and a 2, -1, enter. And finally, it's taken D, so we go back to the matrix, edit menu, and we enter in F. Okay, we're going to call, in our calculator, we're going to call F E. So we have a 2 by 2, and the elements are -2, -1, 3, and 0. Alright. Okay. The matrices are entered, and so now we can go back and we can double check our, let's see, which one do we calculate? We did DE. Okay. D was a 3 by 2 and E was a 2 by 2. So we could multiply those. Um, D, E, and again we call this one D and this one E. And so we had a 3 by 2 and a 2 by 2. And so these matched, and we can perform this product. This is what we got, so hopefully I didn't make a mistake. Alright, how do we actually multiply these? Well, we hit second and matrix, and now we stay in the name menu, and we want to select D first from the name menu, and you can see when you hit enter it takes the matrix symbol with a D inside back to the home screen. And now we have to go back to the matrix menu and select E, and we put them side by side as we would with the multiplication of two numbers, and we hit enter, and I was right. Okay, this matches, or I didn't make any mistakes. This matches the matrix that I got. Okay, negative 17, negative 17, negative 7 in the first column. All the numbers match, so I'm glad I did that right. Now we can go through and calculate all of the other products. Alright, so BA and AB, I'll clear that. Second matrix A, second matrix B, and again we're just selecting from the name column, or the name menu in the matrix. And there it is. That would have taken a lot of time to calculate. A, B equals, and I'm not going to write all these out, I just wanted to show you how to do it with your calculator, but we'll compare AB with BA and see if it's the same thing. So we have 23 and 37, negative 9, 30, and 29, and 22, and then we have 13, what is that? It looks like an 82, and a negative 12. Well, what is BA? What happens if we reverse the order of the matrices in the product? If you have them entered into your calculator, it's real quick to calculate at this point. We select B first, and then A, and then enter. We get completely different numbers. Okay, so multiplication of two matrices is not commutative. We get two, I can't see that, 32, negative 55, 16, negative 27, 24. All the numbers are turning out different. 12 and 65. Okay, and I'll just leave it up to you to run through the rest of them. We'll pick one that we know we couldn't multiply. So let's see, BC, we could do that one. CD, or C, here's our D. Okay, this is our D. So this matrix and that one, we said this was a 2 by 3 multiplied by a 3 by 2. Okay, we could do that one. Let's see, what about C? Oh, I skipped one. One of the products that did not exist was BC, so we had 3 by 3, and then C is a 2 by 3, and so these don't match. Alright, so let's see what the calculator does when we try to make it multiply B times C. Clear. We go to our matrix menu, and we select B, and then we go back and select C, enter. Dimension mismatch, error. Okay, you can't multiply them if the columns in the first do not match the rows of the second, which is the case for B, C. Alright, example 5, sort of an application problem. It says a factory has 4 divisions. Each one produces both tennis and football equipment. The production levels are represented by matrix A. Okay, here we are. Here's our matrix. It is matrix A is a 2 by 4, 2 rows, 4 columns. Find the production levels when the production is increased by 17%. Well, real simple. If we want to increase something by 17%, there's sort of 2 ways you could go about it. One is more clever than the other one. So for instance, if we wanted to increase 10 by 17%, one way to do it would be to take 17%, multiply it by 10, and then add it back to 10. And so that would give us 11.7. The more clever way is to take 10 and multiply it by 1.17, sort of like what we did with the simple interest in one of the previous chapters, and in this case you get the same result. Okay, this is just a matter of factoring out the 10. Okay, and I'll show you that real quick just so I do my best to try to convince you. If I factor out the 10 from this expression, I get 10 times 1 plus 0.17. Well, 1 plus 0.17 is the 1.17 that I just showed you. So, more clever way to increase something by 17%. So, what we're going to do here is take matrix A and multiply it by 1.17. And these are the production numbers. And so I have to run through here and multiply all of them by that. Okay. Well, 100 is just going to be increased by 17. But then we get to 90 and 70 and 30, and that's why they make calculators. Okay. Second, quit, clear. Alright. 90 times 1.17, 70 times 1.17, and it may be quicker if we just went and used our matrix menu from the calculator to do this, but I've already committed to doing it the hard way. So 30 times 1.17, enter. I've got my first few numbers, 105.3, 81.9, and 35.1. So let's see, just 4 more numbers to go. We've got 40 times 1.17. We've got 20 times 1.17. And then we've got 2 60s on the end of the second row, so I only have to do this once. Oh. And so we write 46.8, 23.4, and then 70.2 in the last 2 entries in the second row. So there we are. Real simple. We just scalar multiply the matrix that we were given. Okay. What about example 6? It reads, a coffee dealer buys coffee from 3 different countries, country 1, 2, and 3, each of which produce the 2 types of coffee, regular and premium. The amount of each kind shipped are given by the matrix. Okay. So, in other words, if we bought coffee from C2 and regular, let me write this, regular coffee from country 2. Well, regular coffee is in the first row, and country 2 is in the second column, so that would be $145, I'm guessing. Okay. What about premium coffee from country 1? Well, premium coffee is in the second row, and country 1 is in the first column, so that would be $100. All right. Then it gives us the profit per unit. So coffee is sold for the profit per unit for each type given by the matrix B 250 and 475. Compute the product BA. Well, that gives us 250, 475, and then we multiply it times this first matrix we were given. Okay, and what we have is this is a 1 by 2, and we're multiplying it by a 2 by 3. And so the columns match the rows. The columns of the first match the rows of the second. So we can actually carry out this multiplication. But before we do that, we'll go ahead and answer the second part of the question. What about AB? Well, AB would be A, which is a 2 by 3, first, times B, which is a 1 by 2, and then we see that the columns don't match the rows anymore. Columns not equal to rows. So we cannot compute AB. Alright, so we won't worry about that. We've matched the columns and rows, and so we're going to get a product that has the same number of rows as it does rows of the first, columns of the second. So this is going to be a 1 by 3. And that gives us some idea as to how to construct our product matrix, and I'll do this by hand. We take 250, multiply it by 120, and then we add to that 475 times 100. And I'm actually going to run out of room here. Okay, I'll go ahead and calculate all this so I can erase that, and that'll leave us with a number there. So let's see, 250 times 120 plus 475 times 100, enter, 775. So this turns out to be 775. And now we move on. We say first row, second column. So I'm going to be in the first row. Well, that makes sense because this product matrix only has one row. So first row, 1, and then second column, 2. And I'm in the second column of this this row matrix here. This 775 came from the first row times the first column, so it's in the 1, 1 position. Alright, so we say 250 times 145, and then we add to that 475, price of the premium coffee, times, let's see, okay, the amount, 165. And then if we take the first row and multiply it by the third column, we get the last entry. I'll go ahead and calculate the second column. and that is 250 times 145 plus 475 times 165. Enter. 1146.25. 1146.25. Oh, eraser's too big. 1146.25. I'll try to write that a little neater. Alright, and now this last entry, so it's just going to be 1, 2, 3 columns. 1, 3 would be, and I'll write it up here, 250 times 95, and then add to that 475 times 110. What do we get out of that? Calculator time again. 250, and I got to multiply, times 95 plus 475 times 110. I didn't put my multiplication in there, so fix that. Enter. 760. Okay, so let's see. This is how much profit we're going to make from each country. Okay, we get 250 profit from regular coffee and 475 profit from premium. So we're going to make more more profit from country 2, and that just has to do with the fact that we get more coffee from country 2. We had 145 of the regular and 165 of the premium, which is where we get most of our profit, the premium coffee. And I encourage you to check this with your calculator. Hopefully my answers turn out to be correct. That's it for this video. You got any questions about it, feel free to come by my office. And then also notice that there's exercises below. If you finish up with your WebAssign, you can work these, and if you get stuck on one, again, come by my office, or maybe go to the tutoring lab if I'm not available, and get your work or your answers checked. Alright, thanks for watching.